Hello everyone. Today's topic is ANOVA for evaluating variability in multi-branch batch chemical process outputs. Introduction to ANOVA in chemical processes. ANOVA, analysis of variance, is a statistical method used to compare the means of multiple groups to determine if they are significantly different. It is widely applied in evaluating variability across different batches in chemical manufacturing. Understanding variability helps improve process control and product quality. Importance of variability assessment. Variability in chemical process outputs can impact product consistency and compliance. Identifying sources of variability allows for targeted process improvements. Reliable statistical analysis ensures informed decision making in process optimization. Fundamentals of ANOVA. ANOVA partitions total variability into components attributable to different sources. It tests the null hypothesis that our group means are equal. A significant ANOVA result indicates at least one group mean differs from the others. Types of ANOVA relevant to chemical process. One-way ANOVA compares process outputs across different batch groups with a single factor. Two-way ANOVA considers two factors simultaneously, such as temperature and catalyst type. Repeated measures ANOVA is used when the same batches are measured multiple times. Assumptions of ANOVA. Data within each group should be normally distributed. Variances across groups should be regularly equal, that means homoscedastically. Observations must be independent of each other to ensure valid results. Then, experimental design for multi-batch processes. Proper design involves randomization and replication to accurately estimate variability. Batches should be selected randomly to avoid bias. Replication within batches enhances the reliability of variability estimates. Data collection and pre-processing. Collects sufficient samples from each batch to capture process variability. Screen data for outliers or anomalies that may distort analysis. Ensure data meet ANOVA assumptions before proceeding with analysis. Conducting a one-way ANOVA. Calculate group means and overall mean to understand data distribution. Then compute between group and within group variances. Use F-test to evaluate whether differences among group means are statistically significant. Interpreting ANOVA results. A significant p-value, typically less than 0.04, suggests differences between batch means. Non-significant results imply no strong evidence of variability among batches. Post-hoc tests can identify specific groups that differ significantly. Then, post-hoc analysis. Techniques like Tukey's HSD compare all pairs of batch means to locate differences. Post-HOC test control for multiple comparisons to reduce false positives. This analysis helps pinpoint sources of variability in process outputs. Variance components and process understanding. ANOVA estimates variance attributable to batch differences. Variance components aid in understanding process stability. High, high between batch variability indicates potential process inconsistency. ANOVA in multifactor experiments. When multifactor experiments influence process output, two-way or multi-way ANOVA are appropriate. This analysis evaluate main effects and interactions between factors. Interaction effects reveal combined influences on process variability. Limitations of ANOVA. Violations of assumptions can lead to incorrect conclusions. Small sample sizes reduce the power of statistical tests. ANOVA does not identify the causes of variability, only its presence. Process capability, complementary techniques. Process capability analysis complements ANOVA by accessing process performance. Control charts monitor process stability over time. Multivariate analysis can handle multiple correlated outputs simultaneously. Practical considerations. Ensure data quality and proper experimental design before analysis. Use statistical software capable of performing ANOVA with appropriate options. Interpret results in the context of process knowledge and operational constraints. Case study. Batch variability in a chemical plant. Data collected from multiple batches of chemical projects showed significant variability. ANOVA revealed that batch-to-batch differences contributed to process variability. Process adjustments were implemented to reduce batch variability and improve quality. Implementing continuous improvement. Regular ANOVA assessments help monitor process stability over time. Identifying variability sources guides targeted interventions. Continuous data collection and analysis foster a culture of process excellence. Summary of key points. ANOVA is a powerful tool for evaluating variability in multi-batch chemical processes. Proper experimental design and data quality are essential for valid conclusions. Combining ANOVA with other statistical tools enhances process understanding and control. Final remarks and resources. Statistical software such as R, Minitab, or GPM filter ANOVA analysis. Training in statistical methods improves interpretation and decision making. Ongoing process monitoring and analysis are critical for sustained process improvement. Statistical software such as R, Minitab, or JPM facilitate ANOVA analysis. Thank you.